Bending stress is induced by bending movement, and shear stress is induced by shear force. There will be shear force and bending movement, which are the internal forces of the material, which are offered by the material to restrict the applied force. That is what we have seen earlier. And now, students, if you see here, the shear force will be acting in this direction. So you can see the arrow marks, yellow color arrow marks on the surface of the beam. So all these things are shear forces, and this is bending moment. And let me go for the another image. See here, students, there will be here it is transverse loads, all perpendicular loads, and here all longitudinal loads. There will be two forces that are offered by the material because of the application of the load. So because of the application of the load, there will be two forces offered. One is longitudinal and the other one is transverse. The transverse load we call it as shear stress, shear force. Okay, shear force, and the stress induced by that force we call it as shear stress. And this longitudinal forces, if you observe the arrow marks carefully, the top arrow marks are tending to compress and the bottom arrow marks are tending to elongate. So we have already seen this, why this happens, and because of this change of direction of the longitudinal forces, we have converted this change of direction as a movement, and we have taken it as a bending movement. See here, if we join these two, we'll get bending movement. Okay, is it clear, students? So we have already seen bending stress, sigma is equals to my by I. We have derived all those things, and we have also solved some problems on that. Now let us go for shear stress. So what is shear stress? We have already discussed that there will be shear force offered by the material like this. Okay, so there will be shear force. All of you listen carefully, students. So let us take a small element of the beam. In the entire beam, let us take a small element of the beam, and the shear force will be acting like this in this direction, downward direction. And to compensate this shear stress or shear force, to compensate this, there will be a complementary shear stress acting longitudinally. So shear stress will not come alone. Shear stress will always be with a complementary stress along with it. See, let me make it little more clear. So there will be downward forces, all these downward forces. So to compensate this, if you assume a small portion of this entire beam, because of this downward portion, what happens to this small portion is this small portion tends to tends to rotate, wherein this rotation will be stopped by another shear stress offered by the material. Similarly, to stop this, there will be another shear stress like this. So there will be shear stress throughout the circumference of this small portion. So shear force will not come alone. Shear force will never come alone. Shear stress will accompany another complementary stress. Okay, students, see here. So because of the longitudinal, because of the vertical shear stress here, there will be complementary shear stress along the longitudinal like this. So to to make it little more clear of this concept, I have just taken an example. So assume a cantilever beam. Assume a cantilever beam. Is it clear, students? All of you are seeing cantilever beam, right? All of you are seeing cantilever beam on your screen, right?
Yes, sir.
Yes, sir.
Okay, assume a cantilever beam made of wooden strips like this. Is it clear? These are all wooden strips, students. Okay, wooden strips, not joined, not glued, just wooden strips. They have placed the wooden strips and is fixed at one end, and a load is applied like this. So if you apply load like this, what happens to them is they will try to okay, if you apply load, they will try to slide on each other like this. Is it clear, students? So if you apply a point load at this end, they will try to slide on each other. You can observe here. So they are sliding over each other. This sliding, we call it as shear stress. See, we have not glued them. అంటే మనం అన్నిటిని అతికిలేదు, జస్ట్ strips separate గా strips పెట్టినాం. Separate wooden strips were placed and are fixed at one end and a load is applied like this. So there will be sliding between the material because of the application of this load. So this sliding, I'm calling it as shear stress. So uh, let me show you another figure, right? So now our beams or our elements will not be like this. See, our fibers will not be that loose which can slide over each other. Our fibers will be fixed. So what I have done is I have glued these wooden strips. Okay, I have glued these wooden strips and I have made like this. So I have glued these wooden strips and I have applied a load and I have applied a point load. See, all of you see here, I have glued them. So this will not move and I have applied this force. So where will the sliding motion go? So where will the sliding motion go? In the previous example, we have seen that they will slide because of the application of the force. So here, this sliding will disappear and this sliding will be equals to the shear stress induced within the fibers of the beam. Is it clear, students? This is what I am saying it as shear stress. So shear stress will be induced within the fibers of the beam like this. Is it clear? So this is what I mean to say. Now uh, you might have observed this kind of thing, students. So if you take a wooden plank like this and apply a point load, there will be shear failure. You might have seen this. You might have seen this in your live examples. See here, there is a crack in the wooden beam. So this kind of crack is caused because of the shear stress induced in the beam because of the application of the load. See, we have already seen bending stress. Okay, so bending stress will be maximum at the where bending stress will be maximum at the extreme fibers. Bending stress is maximum at the extreme fibers and will be zero at the and will be zero at the neutral axis. That is bending stress. Whereas shear stress will be maximum at the neutral axis. Shear stress will be maximum at the neutral axis and will be zero here and will be zero here. Is it clear, students? So there is a lots of difference between shear stress and bending stress. So bending stress, while solving bending stress, we have taken pure bending, and there is absence of shear force. అసలు shear force అనేది అప్లై కాలేదు, మొత్తం ప్యూర్ బెండింగ్ ఉంది అని అజ్యూమ్ చేసుకొని we have taken that element which is tending pure bending and we have solved simple bending theory. Whereas here we have seen shear stress. So why is it maximum at the origin? అంటే ఇక్కడ న్యూట్రల్ యాక్సిస్ దగ్గర ఎందుకు షియర్ స్ట్రెస్ మాక్సిమం ఉంటుంది అనేది విల్ సీ. సో విల్ సీ ఇన్ డెరివేషన్. But you have to remember this important point, students. So let me close this and let me go for the derivation now. Okay. All right, students, what are the observations that we have drawn from the shear stress? So shear stress will not come individually. So if there is shear stress like this, there will be opposite shear stress, and again to neutralize this there will be shear stress like this, and to neutralize this so shear stress will always be like this, students. Is it clear, students? So if there is a stress like this, shear stress like this, and to neutralize this, so because of the application, this will move in this direction. So to neutralize this, there will be another complementary shear stress. And because of this, to neutralize this, there will be another complementary stress like this. So if you assume a small portion of the beam, if you assume a small portion of the beam, small portion of the beam, all right, let me take out this small portion of this beam. So there will be shear stress, shear stress like this, and like this, and like this, and like this. There will be shear stress in all the ways. That is what I mean to say. And as we have seen, if this is made by fibers like this, all right. So if this is made with fibers like this, all of you see here, students. Assume our beam is made with fibers like this, longitudinal fibers joined together like this, and there is a application of load, and there will be shear stress. There will be shear stress like this. Okay, and this shear stress will be maximum at the neutral axis. At the neutral axis, this shear stress will be maximum, and at the extreme portions it is zero, because you can see there is no sliding happening here. Okay, this material slides over here and shear stress is happening here between these two, but there is no shear stress here. And if you consider this cross section, all of you see here, students, this is a beam, and if you
Sir,
consider the cross section of this beam, yes, Pani?
కొంచెం థిక్గా రాయండి సార్ కంటి.
Okay. Is it okay?
ఎస్ సార్.
Okay. If you consider a section of this beam, all right, I've just made a section to this beam, and I marked the section like this. So this is a neutral axis. What I mean to say is, here shear stress will be maximum. Shear stress is represented by tau, and tau will be maximum here, and here shear stress will be zero, and here also shear stress will be zero. Why? Because there is no sliding over this. There is sliding here, and there is sliding here, and there is sliding here. So shear stress will be, shear stress will vary similarly as we have seen bending stress varies throughout this depth. So throughout this section, bending stress varies. We have seen it. What we have seen is, if you take a rectangular cross section like this, the shear force will be maximum at the extreme fiber, and will be zero at the neutral axis. That we have seen. Is it clear, students? Have you noticed this? Have you noticed this, students? This should be reverse. Okay. Uh, Let me do this. Did you notice this, students? This is for bending stress. Bending stress. And what I have drawn here is, this is bending stress distribution across the cross section. Bending stress distribution across the cross section. See here, the bending stress is maximum at the extreme fibers, and is decreasing towards the neutral axis here. Is it clear? And has become zero at the neutral axis. The bending stress is zero at the neutral axis, that we have seen because of the derivation and all those things, and we have also solved some problems. Is it clear? Sometimes you will be asked to draw this one also, draw the shear bending stress distribution, draw the shear stress distribution. This kind of questions will also appear. So this is bending stress distribution. Similarly, for I section also you have drawn it, right? So for I section also, this bending stress will be maximum at this portion and will be like this. Okay, so similarly for this also like this, And whereas for T section bending stress, how does it vary, students? Bending stress will be maximum here, okay, and becomes 0. Okay, at the neutral axis it becomes 0. This is how bending stress distribution is. Is it okay? Now let us see about shear stress. Shear stress, we have a derivation of shear stress, students. So I'll just brief you the figure and considerations, assumptions, and then we'll derive it in the next class. Okay, I'll just brief you what shear stress is and all those things. Let me go to the figure. Is it okay, students? Is it visible? Any doubts so far? Anything that you'd like to ask and any difficulties that you have? Kiran?
Nothing, sir.
Okay. So you all have come to a imagination what shear stress is, right? What shear stress is and what bending stress is, you all have got an idea. Akash,
Sir,
is it okay, Akash?
yes, sir.
Okay. So for solving shear stress equation or shear stress derivation, we'll just consider a portion of the beam, a small portion of the beam which is cut horizontally like this. I have cut the beam. I have cut a portion of the beam, and this is Q, R, S, and T. See, the notations are Q, R, S, and T. The length of the portion that I have considered is delta X, and the width of the portion that I have considered is B. So, for our convenience, this is a 3D figure, and this is front view and this is side view. Is it clear, students? I hope you all are aware of drawing. See, I have converted the front view here and side view here. Is it clear, students? So I have drawn the front view and side views. So if you see the side view, this is Q of T and this is R of S. So over the backside of this Q, there will be T, and backside of this R, there will be S. Once again, please see this figure. So I have drawn this side view. Over Q, I have T, and over R, I have S here. And I have mentioned this side view and this front view. So this front view, and I have considered a small elemental area over the section that I have considered. నేను ఒక చిన్న పీస్ని కట్ చేసేసి దాంట్లో మళ్ళీ ఒక చిన్న ఎలిమెంటల్ సెక్షన్ని కన్సిడర్ చేసుకున్నా, సర్క్యులర్ ఎలిమెంటల్ సెక్షన్ని కన్సిడర్ చేసుకున్నా, అండ్ ఏరియా ఆఫ్ దట్ ది డెల్టా ఏ అనుకుంటున్నాను. And I have also represented this circular elemental section in the front view like this as dotted line. Okay, so I have mentioned it as a dotted line. And one more thing is there will be centroidal axis for this entire beam, right? There will be centroidal axis for this entire beam, and the distance of the centroidal axis to the surface that I have considered is y. Okay, see here I have mentioned it here. So y is the distance of the neutral axis from the surface, from the bottom surface of the portion that I have considered. I have considered this portion, students. All of you see here. All of you see carefully. I have just considered this portion. I have considered this portion. Okay, and in this portion, I have also considered an elemental area, elemental cross section of delta A, which I have represented it as dotted lines. So, and that this distance, centroidal axis to bottom surface of the element that I have considered is y. And this is delta x. I have also shown in front view and side views as well. Is it clear, students? Everyone okay with this figure? Did you all got understanding of this? Every notation. Only thing is, if you can read this figure, you can directly derive the equation for shear stress. That is why I'm stressing it once again. So all of you please see the figure carefully and let me know if you have any difficulties in reading this figure. See, I have considered a small cut portion. Okay, small cut portion cut horizontally in a beam. ఒక బీమ్ మొత్తంలో ఒక చిన్న పోర్షన్ ని కట్ చేసి తీసుకున్నాను. ఆ పోర్షన్ బేస్ వచ్చేసి QRST అంటున్నాను. అండ్ ఈ పోర్షన్ ని అంటే ఈ చిన్న పర్టికులర్ పోర్షన్ లెంత్ డెల్టా ఎక్స్ అండ్ విడ్త్ ఆఫ్ దిస్ స్మాల్ పర్టికులర్ పోర్షన్ ఇస్ B. And I have drawn the front views and side views of this small portion, small area that I have considered. ఫ్రంట్ వ్యూస్ సైడ్ వ్యూస్ డ్రా చేస్తే సైడ్ వ్యూ ఏమో ఇట్లా ఇట్లా చూపిస్తుంది. ఈ షేడెడ్ పార్ట్ నేను కన్సిడర్ చేసుకున్నాను. అలా ఈ షేడెడ్ పార్ట్ని నేను కన్సిడర్ చేసుకున్నాను. అండ్ ఈ డిస్టెన్స్ ఏమంటున్నారు అంటే వై అంటున్నారు. ఓకే, ఈ డిస్టెన్స్ వై అంటున్నారు. సో సెంట్రాయిడల్ యాక్సిస్ నుంచి నేను కన్సిడర్ చేసుకున్న పోర్షన్ యొక్క బేస్కి వై డిస్టెన్స్ ఉంది అంటున్నారు. And I have also written some values here, m, v, v plus delta v, m plus delta m అని రాస్తాను కదా. So what I have done is because of the application of the force, because of the application of the loads, there will be loads applied on this beam, right? ఈ beam పైన కొన్ని loads apply చేసింటారు. Because of the application of those loads, and I have assumed that the left side I have got m movement and v shear force. అంటే ఈ పోర్షన్ దగ్గర నేను అజ్యూమ్ చేసుకున్న చిన్న పార్ట్లో లెఫ్ట్కి ఏమో మూమెంట్ ఎం ఉంది, షియర్ ఫోర్స్ ఏమో వి ఉంది అని అజ్యూమ్ చేసుకుంటున్నాను బికాస్ ఆఫ్ ద అప్లికేషన్ ఆఫ్ ద లోడ్స్. సిమిలర్లీ రైట్ సైడ్ వచ్చేసి చేంజ్ అవుతాయి కదా, బికాస్ ఎవ్రీ క్రాస్ సెక్షన్ హ్యాస్ డిఫరెంట్. సి వీ హ్యావ్ సీన్ దిస్. మనం ఒక బీమ్ కన్సిడర్ చేసుకుంటే సింప్లీ సపోర్టెడ్ బీమ్, ప్రతి క్రాస్ సెక్షన్ దగ్గర అట్ ఎవ్రీ క్రాస్ సెక్షన్ వీ హ్యావ్ డిఫరెంట్ షియర్ ఫోర్సెస్ అండ్ బెండింగ్ మూమెంట్స్. Alright. So similarly, I have considered different shear force and different bending moments at this ends. So at this end, what I have considered is I have considered m as my bending moment and v as my shear force, and at this right side, I have considered v plus delta v as my shear force and m plus delta m as my bending moment. Now, if I try to draw the considered portion, నేను కన్సిడర్ చేసుకున్న పోర్షన్ మాత్రమే 3 డైమెన్షన్లో డ్రా చేస్తే ఎట్లుందో చూడండి. సో ఈ చిన్న పార్ట్ని నేను కన్సిడర్ చేసుకున్నాను, దాంట్లో మళ్ళీ ఒక ఎలిమెంటల్ ఏరియా, సర్క్యులర్ ఎలిమెంటల్ ఏరియాని కన్సిడర్ చేసుకున్నాను. సో దిస్ ఇస్ QRST and this is delta x and this is B. I have not mentioned here, students. So this is B. Okay, students, this is B. Now shall we move to the derivation? Derivation కూడా చేసేద్దాం అండి, అయిపోతుంది. All of you please listen carefully. Now force applied on the left end of the elemental area. ఈ నేను చిన్న ఎలిమెంటల్ ఏరియా అనుకున్నా కదా, ఆ ఎలిమెంటల్ ఏరియా పైన ఎంత ఫోర్స్ అప్లై అవుతుంది లెఫ్ట్ సైడ్కి అనేది చూస్తున్నా. సో ఫర్ దట్ వాట్ ఐ వాంటెడ్ టు డూ ఇస్ ఐ జస్ట్ వాంటెడ్ టు రైట్ force applied on the left end of the elemental area. లెఫ్ట్ ఎండ్ ఫోర్స్ అంటే ఏమని రాస్తాం మనము? ఫోర్స్ అంటే స్ట్రెస్ మల్టిప్లైడ్ బై ఏరియా రాయొచ్చు కదా. స్ట్రెస్ ఈజ్ ఈక్వల్ టు, వి నో దట్ స్ట్రెస్ ఈజ్ ఈక్వల్ టు ఫోర్స్ బై ఏరియా అంటున్నాం. నేనేమంటున్నా అంటే ఫోర్స్ రాయమంటున్నా. ఫోర్స్ అంటే స్ట్రెస్ మల్టిప్లైడ్ బై ఏరియా రాయొచ్చు కదా. స్ట్రెస్, బెండింగ్ స్ట్రెస్, దేర్ ఇస్ ఎ బెండింగ్ స్ట్రెస్. సో సిగ్మా బెండింగ్ స్ట్రెస్ అనుకుంటే డెల్టా ఏ ఇస్ ద ఏరియా. డెల్టా ఏ ఇస్ ద ఏరియా ఆఫ్ దిస్ స్మాల్ పోర్షన్, స్టూడెంట్స్. సో ఈ చిన్న పోర్షన్ యొక్క ఏరియా డెల్టా ఏ అంటున్నా. దీనిపైన ఎంత ఫోర్స్ అప్లై అయింది లెఫ్ట్ సైడ్ అంటే సిగ్మా ఇంటూ డెల్టా ఏ ఇస్ ద ఫోర్స్ దట్ ఈస్ అప్లైడ్. సో వీ కెన్ రైట్ సిగ్మా యాజ్, దిస్ కెన్ బి రిటర్న్ యాజ్, సిగ్మా అంటే మనం ఏం రాస్తాం, ఎంఐ బై వై అని రాస్తాం. సారీ, ఎంవై బై ఐ అని రాస్తాం. ఓకే, ఎంవై బై ఐ డెల్టా ఏ. Similarly, let me write the equation for force applied on the right end కి ఏమన్నా రాస్తా అంటే ఈ సిగ్మా ప్లేస్ సిగ్మా ప్లస్ డెల్టా సిగ్మా, నేను అన్ని ఎక్స్ట్రా కన్సిడర్ చేసుకున్నా కదా. సో సిగ్మా డెల్టా సిగ్మా అండ్ ఏరియా రిమైన్స్ కాన్స్టెంట్ డెల్టా ఏ, and this can be written as m plus delta m into y by I is common, constant I mean. This can be written. Now what is the difference of force, unbalanced force? There will be unbalanced force towards the left hand. See here, left hand the force is this and right hand the force is this. So there is difference of force from the left side to right side. So there will be unbalance of force. I just wanted to write unbalanced force. What is unbalance? Net unbalanced force అన్నాడు. Net unbalanced force. If you write net unbalanced force, dF is equals to sigma plus delta sigma into delta A minus right side ఇది minus left side ఇది రాస్తున్న force. Okay, I can write it like this. So if I want to write F, integral over m plus delta m into y by I into delta A minus my by I into delta A. I can write it right. Is it clear, students? So I have just written what is net unbalanced force. So this can be written as this F is nothing but I can take this constant delta m by I integral over y dA. Is it clear? If I simplify the above equation, I will get this. See here, my delta my by I. So delta A can be taken as dA. Delta A becomes dA if I integrate it. So delta m by I into integral over y dA. This is what I have got, and I am assuming it to be 1, equation number 1. Now what I wanted to say is this unbalanced force is resisted by shear stress. Okay, see here, all of you see the figure. I'll just move to the figure. See, there is a difference of force at this point and at this point. Is it right? So here there is a difference force and here there is a difference force on the same element, and but this entire structure remains in equilibrium as stationary. This entire structure remains stationary, but there is a difference force at this point and this point. So if there is difference of force, it has to slide, right? Is it clear, students? Did you understand what I am saying? If there is difference of force here and here, this elemental block, which I have considered very small portion, has to slide over this surface because of the difference of force. But it is not doing that. Why? Because it is restricted. It is restricted by the shear force over here. Is it clear? So this unbalanced force is resisted by the shear stress. So this unbalanced force I can write like this: unbalanced force is resisted by the shear stress. So we represent shear stress by tau. Okay, students. Now what is the net shear force? Net shear force acting on the portion QRST. So we can write net shear force acting on area QRST can be written as tau into A. Is it clear, students? Everyone? Here I have taken a small portion. All of you listen here, all of you see the figure. So I have taken a small portion here and I have derived what is the force over here and what is the force over here by using stress values. So I got two different force values. As there is two different stress value at the two cross sections, there will be difference of force. So if there is difference of force, this block has to slide over the surface like this, but it is not doing that. Why? Because this sliding is restricted by the shear force acting on this area. QRST పైన ఒక షియర్ ఫోర్స్ ఉంటుంది. ఆ షియర్ ఫోర్స్ ఏం చేస్తుందంటే ఇట్ ఈస్ రెసిస్టింగ్ ద ఎలిమెంట్ టు నాట్ టు స్లైడ్. ఓకే, స్లైడ్ కాకుండా రెసిస్ట్ చేస్తుంది. నేను ఏం చెప్తున్నా అంటే ఈ నెట్ అన్బ్యాలెన్స్డ్ ఫోర్స్ ఉంది కదా, ఈ రెండు సెక్షన్స్ దగ్గర ఉన్న నెట్ అన్బ్యాలెన్స్డ్ ఫోర్స్ ఈజ్ రెసిస్టెడ్ బై ద షియర్ స్ట్రెస్ ఆన్ క్యూఆర్ఎస్టీ అంటున్నా. సో క్యూఆర్ఎస్టీ పైన ఫోర్స్ ఎంత ఉంది, షియర్ ఫోర్స్ ఎంత ఉంది అని అడుగుతున్నా. ఇప్పుడు నేను షియర్ స్ట్రెస్ టౌ ఉందని చెప్పినా నువ్వు ఆల్రెడీ. సో షియర్ ఫోర్స్ ఎంత ఉంది, ఫోర్స్ ఈజ్ ఈక్వల్ టు స్ట్రెస్ ఇంటూ ఏరియా కదా. సో ఏరియా ఆఫ్ దిస్ క్యూఆర్ఎస్టీ విల్ బి బి ఇంటూ డెల్టా ఎక్స్, అంతేనా? So this can be written as, this force can be written as tau into b into delta x. Let me take it as 2. Now we can equate 2 is equals to 1. We can equate 2 is equals to 1. We know that 2 is equals to 1. Why? Because this shear force is resisting the difference of force. That is why I am equating. So delta m by I, equation 1 రాస్తున్నా, y into dA is equals to tau into b into delta x. Is it clear, students? Is it okay for everyone? Any doubt so far? Please let me know if you have got any doubt. So from this equation we can write tau is equals to delta m by delta x into 1 by IB into integral over y dA. See students, in this equation, what is integral over y dA? Integral over y dA is the area, movement of area, movement of area. Okay, movement of area, which can be given as, so integral over y dA can be given as a into y bar, ay bar. We can take this as ay bar. We have also seen this in bending stress. Bending stress derive చేసేటప్పుడు integral over y dA ని ay bar గా తీసుకొచ్చి రాస్తాము, where a is the area of the ఇక్కడ చూడండి. So this is the portion that we have considered, and y bar ఏమవుతుందంటే, so this distance becomes y bar. Neutral axis to the centroid of the considered portion is y bar. Neutral axis nunchi centroid of the considered portion is y bar, that we have seen already. And area is a of shaded portion. Okay, so integral of y dA can be taken as ay bar. Now if you take this, and what is this equation becomes tau is equals to, tau can be written as see here, m by x, delta m by delta x అంటే ఏమన్నా రాసినాను మనం. So movement is equal to force into distance అని రాస్తాం కదా, అంతేనా? సో ఇక్కడ ఏమన్నాడు మనకు, మూమెంట్ బై డిస్టెన్స్ అయింది ఇక్కడ, మూమెంట్ బై డిస్టెన్స్. See here, this is delta m, delta x, movement by distance. This can be taken as force. What is this force? Vx. So we can take, and delta m by delta x is equals to Vx, and this tau becomes Vx by Ib into ay bar. Okay students, so this is what the derivation of shear stress is. So we can write tau is equals to Vx into ay bar by Ib. Is it okay, students? Where tau is shear stress, so where tau is shear we are running out of time, right? We'll continue in the next class, students, and please let me know if you have any difficulties as of now. Okay, students, you may leave. We'll continue in the next class. If you have any doubts, please ask.